Hi, and welcome to Codex. We're very happy to have Cynthia Vinzant with us today. She is an associate professor at North Carolina State University and is currently a von Neumann Fellow at the Institute for Advanced Study in Princeton. Cynthia received her PhD from Berkeley in 2011 under the direction of Bernd Sternfels. From there, she held positions at Michigan, Constance, and Simons before moving to North Carolina State in 2015. She has received a number of prestigious awards, including an NSF postdoc, a Sloan Fellowship, and a career grant. Professor Vinzant is an expert in real algebraic geometry and its connections to other fields, including combinatorics and convex optimization. Notably, her research program has resolved conjectures in phase retrieval on the threshold for injectivity, as well as Mason's conjecture on the sizes of independent sets and matroids. Today, we're delighted to have Professor Vinzant speak to us about the geometry of spectrahedra.
Thanks, Emily, and the other organizers for the very kind introduction and kind invitation to speak. So Emily asked me to talk about the geometry of spectrahedra, which I'm happy to do. It looks like I can't see the chat, so if there's a question in the chat, maybe someone can just unmute themselves and ask. Please ask questions if at any point you have questions. So let's start off with just a definition. I'm going to start off with the convex cone of positive semidefinite matrices living inside of the real vector space of real symmetric matrices. So this is the set of matrices, all of whose eigenvalues are non-negative. And a spectrahedron is going to be the intersection of that cone with an affine linear space. Any set that you can get in this form. And that's going to be the main object of the day. Oh no. Is that okay? In particular, if you have an affine linear space, you can parameterize it. Can you see my cursor? Yeah. Okay. So you can parameterize any linear space by a point plus a linear space. And so then you can identify any spectrahedron with the set of parameters that land you inside of the PSD cone. So this will be, say, the set, let's call this a D. So the set of parameters x1 through xd, so that this linear matrix is positive semidefinite. And so one of the big reasons to care about spectrahedra is that these are the feasible sets of something called a semidefinite program. You could take a definition of a semidefinite program to be the problem of maximizing a linear function over a set of this form, over a spectrahedron. So this is a generalization of linear programming being maximizing a linear function over a polyhedron. And has lots of nice applications in combinatorial optimization, control, polynomial optimization, things that hopefully people in this seminar can. Oh, okay. So some examples. Hopefully there'll be a lot of pictures. So any polyhedron is a spectrahedron. If I just take parameterize an affine linear space with diagonal matrices, and a diagonal matrix has non-negative eigenvalues if and only if the diagonal elements are non-negative. So then I just have, any affine linear forms on the diagonals, and I require them to be non-negative. This will define some polyhedron or polytope in this example. But you can also get, more interesting looking sets. So for example, the cylinder is a spectrahedron. I can write it as the intersection of an affine linear space parameterized by this with the set of PSD matrices of 4x4 PSD matrices. So I claim that this matrix, this 4x4 matrix, is positive semidefinite if and only if the point XYZ lies inside of this cylinder. So Z should be between -1 and 1 in order to make these non-negative. And in order to make this little 2x2 matrix positive semidefinite, you'll need X and Y to line the unit circle. So already you get some sort of more interesting behavior. And Another interesting example is something called the elliptope, which we get by just intersecting with matrices whose diagonal elements are all equal to 1. So this is a picture, it's sort of a poofy tetrahedron of the values of x, y, z that make this 3 by 3 matrix positive semidefinite. Okay, and so then what we would want to do is understand, so like polytopes, for example, people understand a lot of things about polytopes. There's a lot of nice combinatorial things you can say, and some of that helps develop, leads to interesting algorithms for linear programming. And so, one can make the case that we want to understand the geometry of these feasible sets of semi-definite programs, maybe with the hope of developing better algorithms. But I think they're also just interesting geometric objects in their own right. So first, to understand these things, let's first understand the PSD cone. So if I have a real symmetric matrix, it's positive semi-definite. There's lots of different ways of characterizing whether it's positive semi-definite. If it's real symmetric, all of its eigenvalues are real. It's positive semi-definite if and only if all the eigenvalues are non-negative, which is equivalent to saying that all of the diagonal minors of the matrix are non-negative, meaning take some subset of rows, take the same subset of columns, and take the determinant of the resulting submatrix. One can also characterize it by saying that the corresponding quadratic form is non-negative on all of Rn. Take any vector in Rn and say take V transpose AV, that's some real number, and I want that to be non-negative for all V. And then the last thing that one can do is, if you have a positive semi-definite matrix, you can factor it. You can write it as some matrix B times its transpose over the real numbers. And in particular, this lets you interpret the matrix in 2 different ways. One is that the entries are inner products between the rows of B. And that the other is that you've written A as a sum of rank 1 matrices, namely the rank 1 matrices given by the columns of the matrix. The columns of the matrix B. Okay. And so maybe before digging into the geometry too much, I just want to go through some of the canonical examples. So one is this elliptope. So I gave you the 3 by 3 elliptope, just pictured here. So this is the set of n by n symmetric matrices that are positive semi-definite and whose diagonal elements are all equal to 1. And it's not too hard to check that this contains 2 to the n minus 1 matrices of rank 1, namely matrices of the form x transpose, where x is a vector of 1 and minus 1s. So for example, for n equals 3, this gives 4 rank 1 matrices, and they correspond to the 4 sort of pointy bits of this poofy tetrahedron. I claim that this actually corresponds to cuts in the complete graph on n elements. Every such rank 1 vector corresponds to a cut, because you're assigning the numbers 1 through n, say a 1 or a minus 1. And then the ij entry of this matrix is just going to be the product of the corresponding numbers. It's going to be a 1 if you gave them the same plus or minus 1, and it's going to be a minus 1 if they were different. And so this was used to give one of the first big applications of semi-definite programming, which was to bound the value of a max cut. So namely, you pick say, non-negative weights on pairs of numbers, 1 through n. And the value you want is you want to split n into two subsets, say S and S complement, that maximizes the sum of all of the things, of all of the pairs with one endpoint in one set and one endpoint in the other. And so the sort of famous Gomans-Williamson relaxation of this says the following. It rewrites this, say, well, you can interpret a cut as an assignment of everything 1 through n to either -1 or 1. And then what does this give you? So if you look at this value 1 minus xi xj over 2, this takes value 1 if you've given them different I and j different assignments, and it takes value 0 if you give them the same. Okay, so this is just rewriting the problem. And then that's the same as maximizing over the rank 1 points of this elliptope of this linear function in the entries of this matrix. And so then if you give up on this constraint that the matrix has to rank 1, then you get a relaxation. And so now this last thing is a semi-definite program. You're maximizing a linear function, affine linear function in the entries of the matrix over some spectrahedron, the elliptope. So the famous theorem of Gauss-Williamson is this does well. This gives you 0.87 roughly percent of the optimal value. And yeah, this was one of the big motivating examples to show that sort of semi-definite programming could do something interesting. Another big application is sums of squares of polynomials. So we'll say that a polynomial with real coefficients of, say, degree at most 2d is the sum of squares, if and only if. I mean, by definition, you can write it as a sum of squares of other real polynomials. And you can actually phrase this as follows, is writing f as sort of a quadratic form, a positive semi-definite quadratic form in the monomials of degree at most d. So I claim that f is a sum of squares if and only if there's some large positive semi-definite matrix A, so that f is equal to m transpose am, where m is the vector of all monomials of degree at most d. And this big N is the size, the length of this vector. And just to get an idea of why this, so here's a short sketch of the proof of this. If you have a sum of squares, then everything that you're squaring is some vector. So hi is going to have degree d, at most d. So you can write it as some vector times the monomials of degree at most d. This is just a vector of coefficients. But the square we can actually write out as m transpose vi transpose m. And now this is linear in this rank 1 matrix vi transpose. So we can pull the m's out, and then we're writing m transpose times some positive semi-definite matrix times m. And so what this means is the testing if a polynomial is a sum of squares becomes tractable using semi-definite programming. Just as a very small example, so we take in one variable a polynomial of degree 4, so 2 times 2. So if I take 1 plus t squared plus t to the 4, the goal is to write that as a positive semi-definite quadratic form on the monomials of degree half. And if you write out, so for every coefficient, this gives you some equality. The coefficient of t to the k on one side equals the coefficient of t to the k on the other side. What you get is you have a sort of one-dimensional family of matrices to put here. And this matrix is positive semi-definite on some interval of values for A. I mean, at A equals 0, you get the identity matrix, which corresponds to the way you would want to write this as a sum of squares, namely 1 plus t squared plus t squared squared. But there are others. So for example, if I take one of these endpoints at -1, then I get this matrix. And I can write that as something times its transpose. And then use the columns of this matrix as coefficient vectors for the polynomials I'm going to square. So one polynomial is going to be 1 plus 0t minus t squared, and the other is going to be 0 plus square root 3t plus 0t squared. So the set of sums of squares is actually a projection of the PSD of an appropriate dimension. And if you're willing to take duals, so take the convex dual cone of this, then you also get something interesting. So if instead of sums of squares, we consider all polynomials of say degree 2d that are non-negative, globally non-negative, then you can convince yourself that the dual cone, the set of linear functions that are non-negative on that cone, actually come from moments of non-negative measures on Rn. And since the set of sums of squares is contained in the cone of non-negative polynomials, and duality reverses inclusion, then you have the cone of moments is strictly contained in whatever the dual cone is to this cone of sums of squares.
Hey, Cynthia?
Yeah.
Can you help me understand the notation? You have integral of something subscript something else. What does that mean?
Yeah, so I'm saying, so you have some non-negative measure on Rn, and yeah, so this is a little bit too dense, but so I'm taking every monomial of degree at most 2d, and I'm integrating it against that measure. That's what I'm attempting to put by this very, so this is code for, a monomial of degree at most 2d.
So so that's a number?
So that's a number, yeah.
That's a
so
scalar?
for every non-negative measure, I'm going to get a vector.
You're getting a vector.
Sorry, but the alphas are multi-indices, right?
The alphas are multi-indices.
I see.
So this
X
is
is
really
the
like
large
x1 to the alpha 1, x2 to the alpha 2, all the way through xn to the alpha n. Yeah. It's just
And I'm integrating this vector over this measure on Rn. And I end up with a vector.
Yeah.
Yeah, great, thank you.
Yeah. And I claim that this is, so if you go over all non-negative measures, you actually end up with a convex cone.
Oh, and it's a moment because I'm integrating against a measure. And I see taking scalar multiples are probability measures, probably. Okay.
Yeah, exactly.
Cool.
I
Thanks.
can take convex combinations of them, and then the integral is linear. So this turns out to be a convex cone.
Awesome.
Yeah, this is purposely sort of very sparse because because I'm a jerk. So for example, suppose the measure was just a point mass somewhere. then integration against this measure just evaluates at a point. So for example, I could range over all real values and just take, then the moment at a point mass would just be this vector. The moment vector would just be this. And you know, if I start, and I can also take convex combinations of point masses, and then the corresponding measures will be convex hulls of points that look like this. And so then this this set of measures will be a convex cone. I should have put a 1 here to make it a cone. But it turns out that this is a spectrahedron. So in fact, if you're in one variable, then there's an equality between these two things. Every non-negative polynomial in one variable is a sum of squares. And so then you get an equality between these two things. And in particular, you can write it as a spectrahedron. So for example, if I take the convex hull of just t squared, as t goes over r, that's a parabola. Convex hull will be the stuff above the parabola. This is a spectrahedron. This is the set of x1, x2, so that this little matrix is positive semidefinite. And then it's not so exciting for this example, but if I want to minimize some polynomial of degree at most 2d, I can view that, writing out the vector of coefficients of this, I can view that as minimizing an affine linear function over this set. So this, I can view this as a semi-definite program. Just to go, you know, slightly more exotic, I can also do this restricting to some set, like an interval. So if I take the convex hull of the curve, parameterize t squared, t cubed, as t goes between -1 and 1, it turns out I can also write this as a spectrahedron. This is an affine slice, a 3-dimensional affine slice of the cone of PSD 4x4 matrices. And I'm not exactly telling you why, but the high-level picture is that it has to do with, it's sort of the dual picture to this sum of squares argument that I made before. Yeah. And so then minimizing or maximizing a polynomial of degree at most 3 over this interval, one could instead minimize an affine linear function over this spectrahedron. For univariate polynomials, this does not seem like a good idea, but then as you go higher, this gives you a good relaxation for your problem. One of my other favorite examples that I thought people might appreciate, you can do the same thing with trigonometric moments. You can take the convex hull of points of the form cosine theta, cosine 2 theta, cosine 3 theta. And this is also a spectrahedron written using topoless matrices. This is equal to the set of x, y, z in R3. The convex hull of this little curve segment is equal to the set of x, y, z that make this matrix positive semidefinite. Can be, if none of the rest of the talk makes sense, you can try and figure out why that's true. And you get interesting, you know, things, convex bodies. Okay. And so one thing we want to do is you know, understand the geometry of this thing. And at least for me, it makes sense to understand them from the point of either algebra or convex geometry. So just as a crash course on real algebraic geometry, so a basic closed semi-algebraic set is something defined by some polynomials. So it's a set of, say, P and Rn that make some collection, G1 through GS, of polynomials non-negative. And both the PSD cone and any spectrahedron, I claim are examples of this because if they're given by the non-negativity of the diagonal minors of this matrix, which are perfectly good polynomials in the entries of the matrix. And a semi-algebraic set, more generally, is something you can get by taking finite Boolean combinations of basic closed semi-algebraic sets. So you're allowed to take complements, intersections, unions. A unit disk is basic closed, a square is basic closed, but if I take their union, it might not be basic closed. You have a hard time writing this set as in this form. And one of the fundamental theorems in real algebraic geometry is if you take the projection of a semi-algebraic set, the thing you get is semi-algebraic. So for example, if I take the diagonal minors of this triplets matrix I had before, I write down my spectrahedron S using these polynomial inequalities. And when I project, say, onto the X and Z coordinates, I still get something semi-algebraic, but I might need to use a union of two sets that I can write. And in fact, so this, you can't get away from this union, unfortunately. Like you can't write this down without a union here. And so in fact, that shows that this set, this projection, can't be written as a spectrahedron. You can't write this as the intersection of some of a PSD cone with an affine linear space, which is interesting. Another thing, so from convexity, something you might use to study, so that was the whole crash course on real algebraic geometry. From convexity, something you might be interested in for a convex set is its extreme points. So the set of points that you can't write as a convex combination of other points in the sets. So this is a collection of convex sets I've shown you so far, and in blue are their extreme points. And if you have a convex compact set, then the Krein-Milman theorem says it equals the convex hull of its extreme points. So everything else can be written as a convex combination of its extreme points. If you have a cone, then you can do something similar for cone, for rays of a cone. So an extreme ray is a ray. So it's a point plus scaling, and it's extreme if you can't write it as some convex combination of other rays. And so this is something you could ask about for any convex set, and we'll be interested in asking about it for the PSD cone and for spectrahedra. More generally, a face is some subset, so that if you take a convex combination of points and you land in that subset F, then you must have started in that subset F. So for example, if you take a convex, so this edge of the square is a face of the square, as you'd hope. And if you take a convex combination of 2 points and land, say, on the edge of the square, then those 2 points must have come from somewhere on this edge.
And the face includes the endpoints in that case?
Yeah, and the face includes the endpoints. So it's just, for polytopes, it's sort of the same as you would think of for faces. And here we see that spectrahedra can have infinitely many faces. I mean, even in the circle. So the any point is a face on the circle. And one way to get a face is to optimize some linear function over your convex set and just take all this set, the set of points achieving, say, the maximum value. Yeah, let's get that. So for example, if we take the PSD cone, we can write this as the convex hull of PSD matrices of rank 1, so vector times its transpose. It's a convex cone, and its extremes are exactly the things of rank 1. More generally, this thing has faces. It gets hard to imagine because it's in quite high dimensional space, but it has faces of dimension r+1 choose 2 as r ranges over 0, 1 all the way up through n. And the faces have the form, they're basically mini PSD cones. The faces are determined by the kernels of their matrices. So all of the faces look like the set of PSD matrices that have some fixed vector space in the kernel. For example, it gets easier if you take the vector space to just be, say, coordinate vectors. And then the set of PSD matrices with these vectors in the kernel is just the set of matrices with a R by R PSD matrix in the top left and then zeros everywhere else. And that's isomorphic to to an R by the PSD cone of R by R matrices. So you have many, you have many families of faces, but the dimensions of faces you have these weird jumps, right? All of the faces are isomorphic to smaller PSD codes. And then so the faces of Spectrahedra are also characterized by kernels of matrices. So for example, for the cylinder, if we looked at all of the matrices with the vector E3 in the kernel, so all of the PSD matrices of this form with E3 in the kernel, that basically means this entry needs to be 0. So then we get a 2-dimensional face, namely the top of the cylinder, given by Z equals 1. Whereas if we take the set of matrices with, say, E1 in the kernel, that's going to pick off, on the circle that picks off the point, let's pretend this is the point x equals 1, y equals 0. That's going to pick off this whole edge. We don't care what Z is, but x equals 1 and y equals 0. So that's going to give us an edge on the cylinder. And if I want both of these vectors to be in the kernel, then I'm going to pick off their intersection, just a single point. And there's actually a nice characterization of extreme points of Spectrahedra. Let's see if we can explain this. So you have various parameters going on. You have how many, so the dimension of your set, which is going to be D. So in almost all of the pictures I've shown, the dimension is 3. There's the size of your matrices. And then, so we have this spectrahedron. If it's compact, then it has extreme points. And we could, if we look at an extreme point of this convex body, there's some matrix associated to that. And we could look at the rank of that matrix. And the ranks actually are fairly constrained. So D is the dimension, N is the size of the matrices. The ranks always satisfy the following, the extreme rank, the rank of an extreme point always satisfies the following inequality, which gives an upper bound on R. It says R can't be too big. And furthermore, if you sort of pick generic matrices for most choices of subspaces to intersect with your PSD cone, you also weirdly have a lower bound on R. So if you, assuming that I haven't made any typos, this inequality should give a lower bound on R. If we make R bigger, this gets smaller. And Gabor Pataki, who's a mathematician at UNC Chapel Hill, sort of one of the first ones to study this. And so this interval of ranks is usually called the Pataki range. And it's the, and you imagine if you're taking extreme points, these are the things, these are the matrices you might end up at if you solve a semi-definite program. So for example, yeah,
I hadn't seen the lower bound before. So like people like to solve SDPs quickly with the promise that the extreme point that they're looking for is low rank.
Mm-hmm.
And this is saying that for generic SDPs, slow your roll, not so fast. Like
yeah, so this gives a range where the ranks could be. Yeah, it doesn't make any promises beyond that.
mm-hmm.
Let me do an example, and I think that will help, hopefully. So like for the elliptope, if you go through the inequalities you had before, then it's not so impressive here, but so the potential ranks that you could get of an extreme point are 1 and 2. And 1 are these sort of pointy, there's 4 things of rank 1, we said, and they're these pointy ones. And then all this round surface are things of rank 2, you can check. And the sorts of promises that people would want to make are that you hit the rank 1. It's good if you hit the rank 1 matrices, which you will some of the time. Because they're quite pointy. If you imagine optimizing a linear function, you have a good shot at hitting one of the rank 1s. But sometimes also you hit these curved bits. And yeah, also this thing is only for for generic linear slices. So maybe if you're doing some special problem, you could say something even stronger if you're optimistic. Yeah. So for d equals 3 and n equals, the matrices here are 4 by 4. The ranks you'd expect to see are 2 and 3. And the extreme points of this thing are just the points on the circles, the 2 circles on the top and bottom. And if I take a point here, then the top 2 by 2 matrix is going to drop rank by 1, and one of these 2 is going to be 0. So I'm going to have something of rank 2. So there are things of rank 2, but there are no extreme points of rank 3. Because we just went through all of the extreme points, they all had rank 2. But there could have been. That's what this is. Yeah, but then you can also, if you do something special, like this example, here there's actually matrices of rank 1. But because this is sort of not general, we picked something very special. Like if we take everything equal to 1, we get a rank 1. That's this guy up here. So even though the Pataki range says that we should expect things of rank between 2 and 3, if we pick something special, we might hit things of even lower rank. Does that sort of answer your question, Dustin? yeah. There's a lot of, as to which ranks show up, it's not so easy to say. And there's a lot of interesting math that goes into such questions. One of my favorite comes from examples like the elliptope. So here, if we're taking, we're considering 3 by 3 matrices, and we take something, a 3-dimensional slice of the 6-dimensional cone of 3 by 3 matrices, we expect to find extreme points on this thing of rank 1 and 2. And so one could ask whether or not rank 1 matrices show up. So that could be the question. Like, you take a 3-dimensional slice of 3 by 3 PSD matrices. Did you hit any rank 1 guys? So if you're an algebraic geometer, what you might do is count dimensions of things. The set of rank 1 matrices is codimension 3. So if you take a 3-dimensional affine slice, you expect to hit it. And yeah, so you could, and it's degree 4, whatever that means. And so what this means is that your options are, you have 0 through 4 or infinitely many rank 1 matrices. And sort of you should expect to get 0, 2, or 4. And in fact, you can show that 0 is impossible using something from topology, which I find interesting, and I think relates to, I don't know, things that relates to arguments you might have seen before. So I claim that you're always going to get a rank 1 matrix in a slice like this. And the argument comes from topology. Is suppose you didn't. You took a 3-dimensional slice of the cone of 3 by 3 real symmetric PSD matrices, and you look at the boundary of this thing. You have a 3-dimensional convex body. Its boundary should look like a sphere. And if there's no rank 1 matrices, we can define a map from the boundary to the real projective plane, given by take a point on the boundary of this sphere. And because it has rank 2 necessarily, the corresponding 3 by 3 matrix has a unique kernel up to scaling. And this is going to get, and you vary around the sphere, and the kernel should change continuously. So this would necessarily give an embedding of the sphere into the real projective plane. But topologists tell us that you can't do that. So that means that this, whatever slice you took, there must be a positive semidefinite rank 1 matrix. In the elliptope, we happen to find 4. There's examples with 2, but you're not allowed to get 0. That's sort of what topology says. And there's more sophisticated tricks that you can use like this. And I'll point to a paper from 1984 for such things. But this is an example that, like, sort of, to me, this is saying that unexpected pieces of math sort of come into play for the geometry of these things. Okay. Yeah, maybe I'll skip over the slide. So the other sort of piece of geometry that is interesting is we might also be interested in projections of these convex bodies. And as we saw before, if you take a spectrahedron, so you take the PSD cone, you slice it with an affine linear space, and then you take some linear projection of it, the result might not be a spectrahedron, which is very different than polytopes, right? If you take a polytope and you project it, you're going to get another polytope, which is a little worrying if you're coming from the land of polytopes. And similarly, taking the dual, the convex dual of a set, So the class of spectrahedra are also not closed under convex duality, which is a little worrying if you're coming from the land of polyhedra. But projections of spectrahedra are also things that we can optimize over. If you want to optimize a linear function over a projection of the cylinder, then you just take the linear function and lift it to the whole cylinder, and then use a semi-definite program. So one could also hope to understand the geometry of projections of these things. Sometimes this is called a spectrahedral shadow. So if you take a spectrahedron and then you take it the image of it under some linear map. These are also convex and semi-algebraic. And the sort of class of sets you can get this way are closed under everything, all reasonable operations. Projection, duality, you take the union of two and take their convex hull. And in fact, there was a long-standing conjecture that if you have anything that's convex and semi-algebraic, then you can write it this way. Then you can find some spectrahedron and maybe some giant dimensional space that projects onto this thing. It was actually disproved, I guess, maybe 5 years ago now. And the counterexample was actually the set of non-negative polynomials of degree at most 6 in 3 variables, which is a full dimensional convex cone in a large dimensional vector space. I think there's a few smaller counterexamples known, but it's still it's not very well understood sort of what things come this way. Yeah. So maybe I'll just end. That in terms of, so I've gone over some of the geometry of these things. There's some things known, like ranks of extreme points have bounds, and we know how to characterize various spaces, but there's a lot of interesting sort of open questions about the structure of these things. What ranks can show up as extreme points? Yeah. So if you think about all that's known about polytopes and polyhedra, it's quite a lot. So for example, one could ask for the F vector of a polyhedron, like the number of faces of each dimension. And spectrahedra, you now have infinite families of faces. So it becomes more difficult to characterize what can sort of show up. I think it's interesting. It draws in a lot of interesting math. So I think that's the end. Thank you.
Thanks to Cynthia. If you want to hit that react button.